Okay, welcome back, everyone. Our next talk will be by Anurag Sahay from Purdue, and he'll tell us about shifted convolution of divisor functions in FQFT.
Thank you for the introduction, and thank you to the organizers for the opportunity to speak. So I'll be talking about joint work in progress with Alexandra Floria, Matilda Lalin, and Amita Malik. And on that blackboard, I have a Rosetta Stone for you. So if you don't know anything about function fields, the left-hand side of that is the integer setting, and the right-hand side is what the analogous thing in function fields is. And if you know nothing about function fields, maybe you can entertain yourself by convincing yourself about one of those or one or more of those equivalences. And I'll say more about some of them when they come up. Okay, so before I start talking about function fields, I want to recall for those who don't know about it, the problem in the integer setting. So I'm gonna phrase it in a way so that it's more reminiscent of what Shatalal spoke about yesterday. So you take h to be a non-zero number, and you look at solutions to this determinantal equation x1, x2 minus x3, x4 equal to h. But instead of soup norm or anything like that, I have this weird constraint that x1, x2 is between 1 and capital X. Okay, so I'm just counting the number of solutions to this equation. And this is a strange way to write it, but maybe a more natural way to write it is like this. So you can write it as the sum of integers going up to x of the divisor function, the number of divisors of n, times the number of divisors of n plus h. Maybe this should be x3, x4. Yeah. So here what I'm doing is I'm writing n equals x3, x4. So the summation variable is 1 through x, and x1, x2 becomes n plus h. So the number of solutions is exactly this quantity. So you should think of this as a correlation, right? So I'm gonna maybe divide by 1 over x, so that this is like an expectation of some quantity. Now you can ask yourself, well, what is this? What should you expect this to be? So if you look at the average value of the divisor function, it's not hard to see that is the logarithm of x, right? So the expectation should be, if these two are independent of each other, you should get something which is log squared of x, but they're not really independent of each other, right? So if n is divisible by 2 and h is even, then n plus h is also divisible by 2, for example. So there is a local factor that comes up, which is 6 over pi squared sigma minus 1 of h. This is the same factor that Shatatal had, except he wrote it as sigma of h over h, and maybe I should have an absolute value here. Okay, so this is what you should expect. And in fact, this is what, this is an old problem, first looked at by Ingham, who proved this, what I have written over there, in 1927. This was looked at again a few years later by Esterman. So I'm gonna call this, let's give this a name. So let's call this S of h, for shifted convolution, I guess. So Esterman looked at this problem, and he found an expansion for the whole thing. So this was 31. So Esterman proved that S of h is P2 log x h plus big O of x to the minus 1 over 12 times log x cubed. So here P2 is a polynomial is a polynomial of degree 2, which depends on h, right? So the coefficients of this can depend on f of h, and the first term will be will be this exact coefficient. So it'll be log squared x with that coefficient. And the way he proved this was by exploiting some cancellation coming up in Klosterman sums. So it's very, very near to Klosterman's original introduction of this of his sums in his work on binary quadratic, on quadratic forms. Okay, so I'm interested in what happens when h is growing with x. Okay, so everything I've written is h is fixed. So what happens when h is growing with x? And one reason to be interested in this problem is because of connections to moments. So if I look at the 2kth moment of the zeta function, so this is, you can use approximate functional equations for the zeta function. So this is sort of like, you'll have m and n going up to t to the k over 2 of dk of m times dk of n over mn to the half. And then you'll have, this is zeta times zeta to the k times zeta to the k conjugate. So here you'll have m over n to the it. And if you see this integration over t, the only thing it depends on is m over n. So the effect of this is, if m and n are very far apart, there will be a lot of oscillation in the sum, and it will basically disappear. But if m and n are close to each other, so if say m is equal to n, then there's no cancellation, so you get a main term. So it sort of localizes to things where m minus n, which I'm going to call h, this is small. Okay, so small growing in, I don't remember what it comes down to be, maybe something like that, maybe with a plus epsilon. And so you can make a change of variable m equals n plus h, and then maybe it sort of becomes clearer that there is a shifted convolution over here, and the value of h is also growing with the divisor function. So this is the original motivation for many people to look at this problem. Okay. What do I want to say about that? So actually, I think this connection to moments is due to Atkinson, although maybe people have forgotten that. And this was used by Heath Brown in his fourth moment paper. So I guess this is 79. So as part of his full asymptotic for the fourth moment, he proves that the shifted convolution sum is given by p2 log x, so the same main term. And he has an error term which looks like x to the minus 1 over 6 plus epsilon uniformly in h. Which can go up to x to the 5 over 6. Okay. Now, many people have worked on this problem, so I don't want to say much more about it. Maybe I'll say that Deshoulier and Ivanets introduced spectral methods into this problem. And they use the Kuznetsov formula, and many people have worked on it, including Motohashi, for example. So I don't want to write all of that down, but maybe one thing I will write down is the best result in terms of how large can you take n. So this is due to Merman in 2001. So he proves he gets an asymptotic for h going up to anything smaller than x squared. Okay, and so he can let his h be actually bigger than the summation variable, going all the way up to x to the 2 minus epsilon. Okay, any questions so far? I think so, but don't quote me. I'm not that familiar with that literature. Yeah. Okay, so before I start talking about shifted convolution, before I start talking about function fields, let me maybe tell you how these things go. So and the approach I'm going to show is very classical. It's due to Esteman. So the idea is you want to understand this convolution, and your opening gambit is to open this divisor function. Okay, so you can write this as the summation g divides n plus h of 1, but you don't want to open it like that. You want to use the fact that there is a duality between divisors of a number, which many people have talked about because it's what underlies the DFI delta method. And if you use that duality, you can basically put a 2 here at the cost of putting a size constraint on H, which helps later. Okay, I mean, maybe you need to be more careful when n plus h is a square, but I will not focus on what happens then. So when you do this, you can interchange summations to get a sum over G, and now this will go up to the maximum of x to the half and h to the half, and because h can be bigger than x, or even x, you do need to account for this, of summation n going up to x, the divisor function, but it's now this constraint that G divides n plus h will become a congruence constraint, and you get n congruent to minus h modulo G. Okay. Now, if you're an analytic number theorist, maybe you see a congruence condition and you want to throw a character in. So you detect this condition using additive characters. So this is the same G sum and the same n sum, but now the constraint over this goes away. And inside you have 1 over G times A mod G of the additive character A plus A of F plus H over G. Okay. So let me just focus on what happens in the n term, n sum over there. So if you push the sum over n inside, it looks like this. Oh, sorry, I've gotten so used to function fields that I put F instead of n. Yeah, so it's still n right now. Okay, so you get this. And for many of you, maybe this is something you do in your sleep. What you do now is you apply Voronoi summation to convert this into a dual sum, right? So a Voronoi summation will convert this into a dual sum, which has the same shape, but now the sum will go up to G squared over X, and here instead of Ea n over G, you'll get A bar n over G, where okay, so A and G could be co-prime, could have common factors, but you can deal with that. But assuming A is co-prime to G, you get something like this, where A bar is the multiplicative inverse of A modulo G. Okay, so this is where the Clusterman sum comes in, because you have a sum over A over there. So when you put it together, you can maybe see that there's a Clusterman sum which looks like S of I guess H N G showing up. Okay, so this is maybe child's play for many of you. In any case, so the results of, for example, Esteman, they work with using some bounds in of sums over Clusterman sums that are available at that time, and Heath-Brown's result depends on bounds coming from the way bound on Clusterman sums, and all of the later work comes on using spectral theory to exploit cancellation even over the moduli. Okay, so let me pause for questions before going on to the function field stuff. Any questions? Okay, so let me now write down what is the function field analog of this problem. So for that, let me go to my Rosetta Stone. So the function field analog for most problems, you replace Z with the most simple function field. So it's you look at the polynomial ring over FQ, where Q is a prime power. So if you're not comfortable with that, you can think of Q as a prime. So this is polynomials which have coefficients in FQ. So the integers in Z, they correspond to polynomials in FQT. So I will write F for the polynomial from now on. So you can ask a question, what are the units in these rings, right? So the units in Z are just plus and minus 1. They're the only things which have multiplicative inverses. It's not so hard to show with a degree calculation that the only units in FQT are the constants, right? So things which are just non-zero constants. So things which are which don't have any t in them at all. Okay. Now what's the analog for the integers? So one way to think about the integers is the natural numbers. One way to think about the natural numbers is you have the integers. you remove 0. Now you have 2 copies of everything because there's a sign equivalence. So you just forget about the negative stuff, right? So what's the analog here? You remove 0, you have q minus 1 copies of everything because the first term has some coefficient, right? So these polynomials, these will be something like ad t to the d, and this will be an element in fq times. So you just forget about that, right? You set that to be 1. So that gives you monic polynomials, and that will be the analog for integers. Okay. So the last few things I need to discuss is the notion of size, right? So you have a notion of size in the integers, which you inherit from the metric in the reals. That's not very useful in FQT. So another way to think of the size of an integer is you can think of it as the size of the residue ring Z mod and Z, right? So if you define f to be precisely that in this setting, the size of f, so that's the set of polynomials which are like the residues when you divide by a polynomial f, which you can do because it's a Euclidean domain. So how many elements does this have? Well, you've modded out by f, so you have now d choices for your coefficients because you have the 0th coefficient all the way up to the d minus 1th coefficient. So this is equal to q to the degree of f. Okay, so that's the size of f. So you should think of degree of f as being the notion of size. So what's the notion of being of size x? So x is some real parameter, and you're looking at integers of size x. Well, q to the degree of f is discrete, right? It doesn't take values in ranges. It just takes one value around any particular point. So if you want to fix a size, you can just ask for everything of the same degree, and those will all have the same size. So the analog for being in an interval like this is you look at all monic polynomials which have a fixed degree n. And now I apologize for the overloading of n, but I can't help it, okay? So n is the degree in the function field setting, but here it is actually the variable that I'm summing over. And the last thing is, what is the analog for x? So x is the number of elements, more or less, in this interval for integers. And so it's more or less the number of elements in this. And if you fix a degree, you have basically q to the n choices for the remaining coefficients. And so the size of this set is q to the n. Okay? So hopefully this is somewhat believable. And if you believe this, you can write down the analog for this problem. So the sum will no longer go over integers of size x. It will go over polynomials which are of a fixed degree, n. And I have to normalize by the size. So the size is 1 over q to the n. And you're looking at the divisor function of f. So maybe I should add to that what the divisor function of f is. So the divisor function of f is, so this is just q divides, g divides n 1. So the divisor function of f here will be similar. So you're summing over polynomials which divide f. But here you don't sum over negative integers, right? So here you won't sum over polynomials unless they're monic. So every time I write something like this, it's implicit that the summation variable is monic. And it makes sense when you go to the Dirichlet series side of things. Okay, so that's the divisor function over there. And you're looking at df plus h for some fixed h, or not fixed, but some polynomial h in FQT which is not 0. Okay, have I convinced you this is the problem? Any questions? Okay. So let me talk about a little bit the fact that there are now two regimes. So in the integer setting, there's only one variable, x, right, which you can make go off to infinity. Now I want to make q to the n go off to infinity. There are two ways to do it. One way is I could fix the degree, and I could make the size of the field go to infinity. So there are two possibilities. Maybe I should have said this is section 2. Yeah, so there are two possibilities. You fix the degree, and you let your size of the function field go to infinity. This has been looked at before. It was looked at by, so they looked at many things. but in particular, they looked at this. So they looked at, it was looked at by Andrade, Barry Soroker, and Rudnick. So this is a 3-author paper that looks like a 4-author paper. So they showed that if you look at this, maybe I will go to the next board, or maybe let me use this board. So if you look at the average value of this, and you divide by what you would expect if it was truly independent, right? So the average value of D of F times the average value of D of F plus H. That's basically the average value of D of F squared. So they proved that if you take the degree of H to be less than n over 2, less than n, then this quantity actually tends to 1. Okay. So to very quickly recall, in the arithmetic setting, you have a factor which comes from local factors which divide H, right? Here you have nothing like that. And the way you should think about this is, if you ever do this in a problem, the additive arithmetic structure disappears, okay? Like if you fix the finite field and let the field size go to infinity, fix the degree and let the field size go to infinity, the multiplicative arithmetic remains, but the additive arithmetic disappears. So it's based on this idea that F and F plus H, they have different cycle structures, whatever that means. Okay, so that's all I want to say about this setting, because it's not really an arithmetic setting. The other setting is you fix the size, the finite field. So you fix Q, and you let n go to infinity. Okay, and maybe one thing to point out here is that in this problem, even H is not fixed, right? Because it's a polynomial in a different finite field every time. Here you can actually fix the polynomial H. In any case, this is actually the more arithmetic setting, which looks more like the integer setting. And this has also been looked at previously. And actually, it's been looked at previously by many people. So let me list all of them. So it was looked at by Conry and Floria in unpublished work. It was looked at by Gorodetsky in work that only appears in his thesis, his PhD thesis. It was looked at by Katie Wu, who looked at this actually in her undergraduate thesis. And also by Michael Yasimides. I don't know where this is actually. Maybe this is also unpublished. Okay, so what do these guys prove? They prove something which is very surprising the first time you see it. They prove that, so I'm gonna now call this S of H. So they prove that if degree of n, H is less than n over 2. So I want you to compare this to the integer setting. The degree being less than n over 2 is like the H being of size x to the half, like anything of size x to the half or below. Then actually you get an exact formula. So no error terms. It's exactly equal to a polynomial in log of the size. The log of the size is q to the n, so it's just a polynomial in n, basically. And no error terms, okay? So if I get the time, I will try to explain why they're able to prove such a strong result with no error terms. But it is not so surprising if you know a little bit about how the divisor function works in function fields. And my goal in this work and this talk is to extend this range. So how far can I, if I am okay with error terms, which I'm okay with because I'm an analytic number theorist, how far can I make the H go? Okay, so this is the reason I haven't removed this integer setting problem. I'm just going to change the symbols to be the corresponding symbols in the integer setting, in the function field setting. So now I'm looking at f of degree n of the divisors of f plus the divisors of f plus h. Now again, you can, instead of doing this, you can do this. But now again, you want to use the duality of degrees, of divisors. So, at the cost of adding a 2 over here, you can restrict degree of G to be less than half the size, square root the sizes of n and h, which is half the degree of n and h. So it's n over 2, so it's the maximum of n over 2 and the degree of h. Okay, so this sum over G will just be the same sum over G I have over here. What happens to this sum? So it's the same. You get f in degree mn with a congruence condition on it. So f is congruent to minus h mod G of d of f. And now you want to use additive characters. And maybe this is the point where I'll lose many of you, because what is an additive character over FQT? If you know Fourier analysis or finite abelian groups, right? All I'm using is characters mod G. There's nothing fancy happening. And the point is, you can think of all characters mod G as, something which looks like this, where E is a character for the, real completion, not the real completion, the infinite completion of FQ of T. So I'm not going to go into what this additive character is. Suffice it to say that this is Z mod, like FQT mod G, modeled by G is a finite abelian group, so it has some characters, and you can use that to detect this congruence. So when you do this, you get exactly what I have over here. Okay. And so now if you focus on the F sum, this F is over monic, and this is the sum over G outside. So if you focus on the F sum, what does it look like? So it looks like d of F E AF over G. And F is again still being summed over monics. Now, if you're a number theorist trained classically in the automorphic side, you want to apply Voronoi, but there is no Voronoi. Okay, so I'm going to write down what I think the basic new thing in this in our work is a formulation of Voronoi for divisor functions and function fields. So let me maybe write down our theorem, and then I can talk about Voronoi over here. Okay, so the theorem, and I hope to have this out by the end of the year. So I'm going to put 2024. So it says the average value so I'm not going to write down the error term because I'm not really sure what the error term will turn out to be in the end. We know it's little or 1 so far already. So this is P2n of h plus something which goes to 0 as the degree of n goes to infinity, provided the degree of h is less than equal to 4 over 3 minus epsilon of n. So to compare to the integer setting, this is like saying x to the 4 over 3. Okay, and this is unconditional. And maybe I'll say that after you develop the right Voronoi summation formula, this just uses the analog of the Weyl bound. It doesn't use any spectral theory. So I'm a bit surprised by that you can get to 4 over 3 just by Weyl's bound, but apparently that's how it works in the function field setting. And actually, you can go up to Merman's result, degree of h going up to 2 minus epsilon of n, if I assume the Linux-Selber conjecture. The analog of the Linux-Selber conjecture for FQT. So that's basically saying, if you have a sum over moduli in a Klosterman sum, you get further square root cancellation in that sum as well. And now here's a slightly controversial thing. This is apparently proved in function fields, but I don't understand the proof. I've never seen anyone use the result, so I'm a bit I don't understand the statement of the proof. Okay, so there's a book by Piatetsky, Shapiro, and Cogdell where they prove something they call the Linux-Hilbert conjecture in function fields, but I don't see how that is the same as what I would call a Linux-Hilbert conjecture in function fields. So that part is something I'm trying to figure out, and so this is still work in progress. Okay. Yeah, so I already remarked there's no spectral theory in the first one, and the second one, if you know what the Linux-Hilbert conjecture is, it is spectral, right? The work of Piatetsky, Shapiro, and Cogdell is also about spectral theory of automorphic forms over FQT, or over function fields. Okay, so in the time I have left, let me state what I will call Voronoi summation. So for that, I need to introduce the Esteman function. So you take now C comma G is co-prime, and C is any polynomial, and G is a monic polynomial, let's say of degree at least 1. Okay, so the Esteman function for G, this is defined as follows. So this is defined as the sum over F monic dk of F times the additive character AC over CF over G, the whole thing over the size of F to the S. Okay, so if you're familiar with the Esteman function in the integer setting, it's the same thing. You would have n to the S in the size of n to the S in the denominator, which is the same as n to the S, and here you would have E Cn over G. So it's the additive twist of the divisor of the zeta function multiplied by itself k times. Okay, and Voronoi is morally a functional equation which relates d2 of s, at least for degree 2. It's morally a functional equation which relates d2 of s to d2 of 1 minus s, right? So I'm going to state it in that form. But before I do that, I need to make a change of variables here, because in the function field setting, you have this fact that the size of f is always a power of q, right? So you can use that to write this in a different way. So if you set u equals I guess q to the minus s, yeah. If you set u equals q to the minus s, the size of f to the s, this is q to the s, q to the degree of f to the s. Well, this will be u to the minus degree of f. Okay, so you can, it's even though this looks like a Dirichlet series, it's really a power series in q to the minus s. And so if you make that change of variables, so I'm going to change d to script d to indicate that I'm now thinking of it as a function in u instead of s, then the definition is the following. So I've just changed the f to the minus s to u to the degree of f. And now let me maybe get rid of all of this and state the Voronoi summation formula. So G is a monic polynomial with at least degree 1, because it doesn't really make sense when G is not 1, when G is constant. C is anything in FQT, which is co-prime to G. And then for all U in C, and if there are poles, you interpret both sides as having the same pole with the same residue, and even the same Taylor expansion. Then the D2 of U of C over G, this is QU squared to the degree G minus 1 times the summation over lambda in FQ times of something A lambda of U times D2 of 1 over QU of lambda c bar over g. Okay, and you should compare this to what happens in the integer setting. Maybe I should tell you what a lambda is. So a lambda is something which has a Klosterman sum over the finite field. So this is the Klosterman sum over fq, okay? So 1 and lambda are elements of fq, and you're summing eq 1 plus lambda alpha. eq alpha plus lambda alpha bar is what this is. Divided by q plus something which is it's just something. It's a rational function in U. Okay, and if you want to compare this to what happens in the integer setting, so first of all, 1 over QU, right? If U is Q to the S, U is Q to the 1 minus S, then 1 over QU is Q to the, U is Q to the S, then 1 over QU is Q to the minus 1 minus S. So this is actually relating the estimate function from S to S1 minus S, just with the change of variables, so it becomes something that might look less familiar. And the integer setting, it looks like this. So you have some gamma factors, which I won't write down. And then you have a sum over plus minus. And there's something which, the only thing that changes is the sign in it. And over here, you have the dual estimate, not script D, of this times 1 minus S at, again, the sign is the only thing that changes. Okay, and this is, if you apply Mellin inversion, this gives you Voronoi for the divisor function. And so this bit over here, this is like a gamma factor. And I don't really understand why there's a Klosterman sum in the analog of the A plus minus, but the sum over lambdas, it's sort of consistent with this fact that the units are FQ times rather than plus minus. And from this, getting a Voronoi summation formula is not hard because Mellin inversion is just Cauchy's integral formula. So, if I wanted to sum, okay, I guess I deleted what I was originally looking at. So if I want to sum the divisor function multiplied by an additive twist, where f is restricted to having some degree, that's looking at only the coefficient of u to the n in this sum. So you can just use Cauchy's integral formula to pick that out, then move counters and then apply the functional equation and then reverse Cauchy's integral formula and you get Voronoi summation. And there's no smoothing because in function fields you apparently don't need smoothing because of the discreteness of the sizes of variables. Yeah. It's modulo Q FQ. So thank you for asking. So this is KL2 alpha beta. This is summation gamma and FQ times of EQ alpha gamma plus beta gamma inverse. Yeah, classical Klosterman sums over FQ. And I don't really understand why this shows up. I guess there must be some, this is why I was asking in George's talk what the Archimedean analog for Klosterman sums is. And the answer of Bessel functions doesn't help me because this A plus minus S, I want to think of it as a Klosterman sum over plus minus 1, right? Okay. Maybe that's all I'll say about that. And I have 10 minutes, so let's see. Okay, so maybe let me give you a very brief sketch of the proof of this proposition. And if you're familiar with how the proof goes in the integer setting, it will look the same because it is the same. FQT. So what I mean is, so you take a Klosterman sum, which is like SFG, where this is summation A mod G of E AH plus F A bar. Yeah. Okay. Okay, so what's the proof idea? So let me do that here. So let's start with the estimate function. What is this? This is by definition the sum over monx of the divisor function times an additive twist of AC over G times u to the degree of f. Now you open this divisor function. So if you open the divisor function, sorry, there's no AC, this is CF. So if you open the divisor function, now the sum will not be over f, it will be over f1 and f2, which are both monic, the divisors of f. This divisor function will disappear, and wherever I had an f, it will become an f1, f2. Okay. Now you arrange this you stride this according to the congruence class of, okay, I didn't write down which bit, but let's do f2, modulo g. So you can write this as summation a modulo g of, once you do that, if you write f2 in terms, like if you fix the congruence class of f2 modulo g, it doesn't depend on f2 anymore, it just depends on the congruence class. So you will get summation, I guess, f1 and m, and then summation f2 and m, but f2 is constrained to the congruence class a mod g. But now it doesn't depend on f2, so you can put this bit out, and there will be an a over here, which is the f2. And now this u to the degree of f1, f2 is multiplicative in the u to the degree, right? So there's also a u to the degree of f1 here. And here inside I have summation over f2 and m2 in m, where f2 is congruent to a mod g of u to the degree of f2. So what I do is I call this guy the Hurwitz zeta function in the function field setting. So it's not exactly what I would call the Hurwitz zeta function, but I'm going to call this z u a g. Okay, so it depends on the congruence class and the modulus. And once you see this bit doesn't depend on f1, so you can close the f1 as well. And it's something which I've already written down before. So in the expression for dk, if you put k equals 1, the divisor function will disappear. There's only one divisor. There's only one way to write f as a product of one element. So this is actually the divisor, the degree 1 estimate function on the variable AC. Okay, so maybe I will leave this here and write that this becomes a sum a mod g d1 of u AC over g z u a comma g. Okay, so now what you would do in the integer setting if you had done this is now apply the functional equation of this guy and this guy, which is the same as Poisson summation, if you prefer to think of it that way. So you can just apply the functional equation for both things and then follow your nose, right? You have functional equation, you've written it down somewhere, you follow your nose, you know what you have to get. It's not so hard to get it. But then the question is, what is the functional equation for these guys? It doesn't exist it didn't exist in the function field setting. I looked very hard. I don't think anyone has thought about this before. So it boils down to proving a relationship between z u a g and d1 1 over q u a c over g and vice versa. Okay, I have 5 minutes, so I can't really show you the proof of these functional equations or even write down their statements. Let me maybe say what it actually entails. So if you know how it works in the integer setting, the proof of the functional equation for the Hurwitz zeta function is just Poisson summation. Okay, that's really all it is. It's a Poisson summation in a different guise. Here, I tried using that, but it didn't work. What ended up working for us was we guessed what the answer should look like. Once and this took a long time because it took me a while to understand that the sum has to be over units of FQ of T. Because I was like, oh, it should look like this, right? Where did it? Oh, I deleted it. The plus minus, there should be a plus minus, nothing else. But it really is a sum over signs. That's the thing that took a while. Once you've guessed, it has to look like this, that the functional equation has to relate d1 to z with a sum over signs. you can just use linear algebra to guess the answer. And once you've guessed the answer, you can prove it just using additive characters. So just using orthogonality of additive characters over FQ can give you a relationship between this guy to d1 of 1 over QU A over G, and this guy will relate to Z of, I guess there will be a lambda, right? That was the whole point. There's a sign. And here you'll have Z of lambda A comma G. And then you can follow your nose. You can collect together lambda 1. So there will be two different lambdas, one from this functional equation and one from this functional equation. You follow your nose, you collect them together, and you get what I have over there. So in the remaining time, I want to make a few remarks. So this idea, I mean, this proof mechanic, this stuff, it helps you also work with norm-counting functions of quadratic extensions of FQ. So FQ of t. So the analog in the integer setting is maybe the famous example is sums of two squares, right? So if you look at R of n equal to the number of ways to write a squared n as a squared plus b squared, this is also a modular object because it's the coefficient of ls chi of minus chi of 4 times zeta of s, and it has an analogous Voronoi summation. So there have been people who've looked at analogs of sums of two squares in the integer in the FQT setting, and for them there's some, you can't do it naively like this. It doesn't work in the function field setting. So the analog that I think Waxman and Rudnick introduced, or there are a few papers, so I'm not 100% sure who introduced it. So it looks at the number of ways to write f as a squared plus tb squared. So the field extension is fq of t. This is your this is your base field, and you're adjoining to it the square root of minus t. Okay, that's the analog of q adjoint I in this setting. So this sort of idea also gives you Voronoi summation for RF, and you can use that to prove correlations for RF with itself or with something else. And maybe another thing I want to say is, if you look for a proof of the functional equation for Dirichlet functions and function fields, it's not very satisfying if you're an analytic number theorist. Because the way it works is you relate your character to the zeta function of a curve, and then you use the functional equation for the zeta function of the curve proved by Wei. And I was not very satisfied because I don't really understand this relationship between chi and the curve that it comes from, at least the way I think about things. So one byproduct of this work is that we have a proof of the functional equation for Dirichlet functions, which just follows from this thing over here, right? This functional equation over here. You just basically use this guy to use the fact that if chi is modulo g, you can write it as a linear combination of zeta functions or with zeta functions, apply the functional equation of each guy, and then follow your nose. And it gives back the functional equation for the Dirichlet function. And if you know much about, if you've read Davenport, you will know this is the original proof of Hurwitz for the functional equation for Dirichlet functions. I think I'll stop there with 1 minute on the clock.
Thank you so much. What are some questions for our speaker?
You said you are using well-bound for this kind of clustering sum as HFG.
Yeah.
What will be that? So can you
it's the same as the way bound in the integer setting. So if g is prime, it would be 2 times. So square root of the size, right? So the size is q to the degree of f, degree of g. So it will be 2 times degree. If g is prime, it's this. Okay. And if g is not prime, it will have the divisor of bound that it usually does.
Okay. And in Murman's proof, so his reality is unconditional.
Yes.
And here, okay, you are assuming Lening-Selberg.
Yes. Yeah. Yeah. I mean, I just barely understand spectral theory over Q, right? So I don't really understand spectral theory over FQT at all. And part of my longer-term goal is eventually to understand what is happening and see if I can apply that to other problems in FQT. But for now, I'm sort of, like, if you remember my result, I feel it's very interesting that you get beyond X already in just using Waybound, right? Because Heath-Brown only gets X to the 5/6, while here you can go up to X to the 4/3. So I don't really understand why that works the way it does. But this is the result as it is. Maybe by the time we actually finish writing the paper, the result will be different.
And do you think why we can go up to h going up to x square, right?
Yeah.
So for higher h.
Yeah, I don't know. I haven't thought so much about whether you can go up beyond that point. I think even in the integer setting, if you just apply Linux, if you assume Linux Selbug, you can't get beyond that. So I don't know if it's even true beyond x squared.
Okay. Yeah. Thanks.
Thank you. Thank you for the question.
Does it make sense to study an extra average over shifts? And because in the classical setting, that's studied also, right?
You mean average over h?
Yeah.
Yeah, I
Maybe
suppose
get
you can do it. We haven't thought about this yet. Yeah, I mean, so the longer term goal of this project is to look at higher divisors rather than averaging over the h. And we have some stuff, like a lot of this works, but we haven't worked out exactly what the result you get from it is. But I haven't thought about shifts, whether you can average over shifts. Say again?
D of n squared plus 1.
Yeah, great question. I haven't thought about that either. I should say, this paper, this paper I quoted of Andrade, the 4-author paper with actually 3 authors, they look at many problems which are, people have looked at in the integer setting. So like, the average D of p minus 1, the average over prime p, for example. Things like that. They've looked at many analogs of that and worked on it when q goes to infinity. I think there's not been a lot of work on q fixed and n going to infinity in any of these problems. So I forget, there's a paper on D, I think the Titchmarsh divisor problem by people who are here. But there's not been too much work on this sort of thing.
Any more questions?
Yeah, the moment problem is trivial in the zeta function in this setting, right? Because the zeta function for in this problem, it's not very. It's like a basic exercise to show that it's 1 over qu. So all it is a pole at 1 over q. So the pole at s equals 1 and no zeros, and that's it. That's exactly what the zeta function is. So there's no connection to moments that I'm aware of. That's interesting, at least.
So do you have any significance to go beyond x to the power 2 minus epsilon?
No. Yeah.
No?
No, I don't know. I'm not that ambitious.
Okay. Maybe you can, if you go beyond that, I think you can study about the divisor function in short interval. That is the application I can think of. So that's why I think people want to study if they go beyond x to the power 2 minus epsilon.
I see. Okay. Well, right now I'm just hoping to get this out by the end of the year. Maybe I'll think about what you suggested after that.
Yeah, well,
but thank you for the
very
suggestion.
interesting question. Yeah.
I have a quick question. Would this new Voronoi summation allow you to also handle like d of n, d3 of n plus h?
Right. So no, you need Voronoi summation for d3 there, and we have something, but we haven't worked out what that gives for the correlation problems. But I am hopeful that something is possible without spectral theory, but it is also possible there is nothing possible without spectral theory, and we're sort of still working on that. Yeah, well, that's the goal, right? That's where this project started. We wanted to see if we could. That's where this project of Conry and Floria started. They wanted to see if they could do d3n plus 1. That's sort of hard. It's hard even in the function field setting. So I don't have anything to say about that.
Okay, very good. So then maybe we can continue the lively discussion outside during the break. Thank you so much again.